Welcome to our next video for Stat 212. In this video, we're going to talk more about sampling variability, but this time in the context of sample proportions instead of sample means. So a sample proportion is what we might calculate in the context of binary data. So I think we've talked about a proportion at some point before, but we'll kind of more formally define it here. So whenever we're discussing continuous or discrete data, we're often working with the measure like the mean. The mean is something that I can measure when I have kind of this numeric data. But when I'm working with categorical data, especially when I can kind of split my data up into two categories, I might be interested in calculating a proportion, which is really kind of a fancy name for a percentage, or a more formal name than percentage, where maybe I'm interested in calculating what percentage of my responses fit a particular category. So think like a yes/no question or some other binary question here. So if you think about kind of these sample questions written here, was this individual in the treatment group or not? Did this individual test positive for skin cancer or not? Right? These are things that I can't calculate numerical measures for. But I can calculate the proportion of responses that fit a particular category. So for that reason, a proportion is going to be a percentage representing the likelihood of a certain event happening, often written as a decimal between 0 and 1. And so the sample proportion is kind of like the equivalent of a sample mean, but in the context of binary data. And we can use a sample proportion to try to estimate a population proportion. So let's say I only have a sample of people in a particular population, and I ask them this question. I can calculate the proportion in my sample who say yes, but I also realize that there is a population proportion that I'm trying to estimate. So I want to kind of think carefully about how much variability I might see in my possible sample proportions that I could collect here. So we use this notation of p hat for sample proportion, so p with a little hat over it, and we use this to estimate a population proportion, which we typically just notate with p. So let's say that we're interested in the proportion of employees in our company who got a flu vaccine this season. We randomly sample 42 employees and find that 14 did get a flu vaccination. So what is our sample size? Our sample size here is going to be 42. We asked 42 people this question. And what is p hat? That is going to be the proportion of our sample that answered yes. So if our proportion of interest is those who got a flu vaccination, then that would be 14 over 42, which would be about 0.33. So again, we don't know what p is here. So assuming that the company is not more than 42 employees based on the wording, I'm guessing it is. So there exists a true proportion of employees in this company who got a flu vaccine. We don't know what it is, but we do know that 14 out of the 42 that we asked said that they did. And if this is a random sample, if we have found some appropriate way of sampling from this company, then hopefully it's a reasonable estimate. Hopefully it's reasonably close. But how close is it going to be? How much error might I have in my sample proportion estimating the population proportion? So that's where we get into the standard error of a sample proportion. So again, we've seen this notation before. The difference now is, the difference now is that instead of writing SE x bar, I'm writing SE and then this other sample statistic I'm looking at, which is a sample proportion represented with p hat. So I'm really interested in what this is because this is going to tell me how much error I should expect in my sample proportion as an estimate of the population proportion. Okay, so before we get into that, let's kind of go back here for a second. We're working with binary data. We can kind of think of our data as like ones and zeros. We can kind of numetize, is that a word? Quantize something. I should know this. We can turn it into numbers by just changing our yes and no responses to zeros and ones, where 0 typically means no, 1 typically means yes. And we could actually use the standard deviation formula to find the standard deviation of my binary data, which might sound a little bit odd. Like, how do you calculate a standard deviation of binary data? And so I can kind of give you some ideas here. That if, let's say that my binary data, let's think of a couple different examples. Like what if I had kind of relatively equal numbers of each response? So I don't know if that's quite equal, but let's say that I had 50-50. So I'm going to say 50-50. That would be like the most variability that I could have in the context of binary data, meaning that, right, like this is as variable as binary data can be. And that's very different than, say, having, you know, almost all of one response, right? So this would be like, maybe this is like 90-20, or I'm sorry, 90-20, 90-10. And then imagine having like all the same response. Let's say that this is, you know, 0-100, 0% zeros, 100% ones. Okay, so I can represent the variability in this binary data using a standard deviation. It's just that my standard deviation is going to be on a scale from 0 to 0.5. So for this context, the standard deviation, if I were to plug these zeros and ones into the standard deviation formula, let me, this is kind of hidden up here, so let me bring this down a little bit. So maybe I'll do like standard deviation is going to be 0.5 in this top case. In this case, I don't actually know what it's going to be off the top of my head, but it's going to be, so 0.1 would be the mean of this set of data if it's really 90-10. So then I'm comparing 0 minus 0.1 squared plus 0 minus 0.1 squared plus 1 minus 0.1 squared, right? And if I were to do that calculation, I'd get some number that's smaller. So maybe the standard deviation, I'm going to say it's about 0.1, 0.2, something like that. I'll say like 0.2. And over here, the standard deviation is going to be 0. So if I have all homogeneous data, if I have, say, all zeros or all ones, and I plug that into the standard deviation formula, well, the mean is just going to be 1 or 0 or whatever it is that I have, and I'm just going to get a bunch of 0 terms. So the standard deviation would come out to 0 if I have all homogeneous data like that. So you could calculate a standard deviation even for binary data if you turn it into zeros and ones. So we're kind of using that fact here, that the maximum standard deviation for proportions data is going to be 0.5. This is the most variability. The minimum it could be is 0 if we have all of the same response. And we can calculate, there's a shortcut, so instead of using the standard deviation formula on ones and zeros, there is actually a mathematical shortcut here, and that is the square root of p times 1 minus p. And we're going to use this shortcut in the class because there's no use dragging out the standard deviation formula. So this is a shortcut to calculating the SD for proportions data. And again, we're going to wave our hands. We're not going to derive why this works, why it's the same thing as using the standard deviation formula. We're just going to say that it is and be happy with that. The square root of p times 1 minus p will calculate that value for us. Okay, so that's enough about the standard deviation of proportion data, so like the individual responses. What about the variability in my sampler proportion as an estimate of the population proportion? Well, we can use the same formula that we saw before, just with this kind of plug-in, or just this shortcut if we want to. So, so the formula for the standard error of a sample proportion is still going to be sigma over the square root of n. We're just going to kind of note here that we're going to be using the square root of p times 1 minus p over the square root of n as kind of an equivalent expression that we can use. So if we know our population proportion, which again, we're not going to know what that is, but we'll see that in just a second. If we knew our population proportion, then we could plug that in to calculate the variability in our sample proportion here. Okay, so using that, let's go ahead and go back to the flu example. So from the flu shot example, calculate the standard deviation of our sample data and then calculate the standard error of our sample proportion. So what we're going to do is plug in p hat for p for a second. We're going to talk about this in the next paragraph here. Plug in p hat for p, and then we're going to calculate the square root of p hat times 1 minus p hat over the square root of n. And that's going to be the square root of 0.333 times 1 minus that is going to be 0.67 divided by the square root of 42. So if I calculate these values, I get 0.33 times 0.67. I'm doing a lot of rounding, obviously. The square root of that value is going to be 0.4702 in the numerator. I'll just say 0.470 divided by the square root of 42 is going to be 6.48. So that's going to be, so I'm not being super careful about rounding here. I'm just kind of doing it messily. So maybe I would use more decimals if I was trying to be more careful. But if I was trying to be more careful, I'd just use R anyway. But this is just kind of for show here. 0.07. I'll go to 0.0725. So I get about 0.0725 as my standard error for my sample proportion. So I guess I'll write it again here. So that means that given my sample size of 42, given what I observed in terms of p hat and the variability there, an expected amount of error in my sample proportion is about 7%. I estimated it's 33%, but I could very reasonably be off by as much as 7% or even more without that being unusual at all. So there's still a good amount of error, expected error, I should say, in my sample proportion. Okay, but why did we plugged in p hat? Is that a problem? Right, so we talked about that in the sample mean section. If we're plugging in a sample statistic in the formula, if we're plugging in something for sigma, that's a little bit of estimation error. And so in the context of proportions, the answer is yes, it does matter. Yes, it is an approximation, but it's usually a pretty small approximation. So that, whether or not I know p, or if I'm plugging in p hat for p, the amount of approximation error that goes into this is going to be pretty small, and it's definitely going to be very small if I have a relatively large sample. And that has to do with the fact that sigma is going to be bounded by 0.5 to 0, where most of the time I'm going to have a value pretty close to 0.5. And so usually, if I have a pretty small sample, what is commonly done is you just kind of slightly overestimate your standard deviation calculation to be a little bit larger than what it would be if you just plugged in p hat. So if you're using software, it often will automatically do that for you. But honestly, the amount of approximation error is pretty negligible. Even with the sample size of 42, that approximation error is going to be pretty tiny, a pretty negligible amount of error in that calculation. So that's why we don't usually make a big deal about this or talk about it much of plugging in p hat instead of p and why it matters. As long as you just kind of know that the approximation error, like yes, there is a little bit, but it's pretty negligible. And certainly if I have a relatively large sample, like if I had a sample size of 100, it would be almost unnoticeable at that point. So it doesn't really matter too much here. One other thought here, what if we had a smaller company and perhaps the 42 employees we surveyed was actually everyone or all but a few? Would that change anything here? And so I mentioned this because we're talking about calculating a standard error in our sample statistic. We're trying to estimate a parameter. And these calculations are assuming that these are infinite populations, the way that they're set up. However, if we're doing this in real life, we're often working with populations that aren't infinite. There is going to be a countable number of observations in the data. Sometimes they're basically infinite, but many times they're not. So in these cases, it's always good to kind of keep in the back of your mind. This is true for proportions. It's true for sample means as well. The standard error is going to overestimate your error when your sample size is a noticeable, I'll say a noticeable percentage of your population. And I kind of put it in this box down here that some people kind of put the mark at 5%, some people put the mark around 10%, but once we get into that range where our sample comprises about 5 to 10% of our population size, you're going to notice that your standard error formula will begin to overestimate how much error you have in your sample statistic. So again, it's because the methods we're assuming, these formulas work if we assume an infinite population. If we don't have an infinite population, then we start to see some departure here between our calculated standard error and what the actual standard error is if we sample repeatedly from this population and just observe what happens. So just kind of keep that in the back of your head that this is the case. All right, let's look at another example here. I think this is a really interesting question. I love to use it to think about sampling variability, especially in the context of sample proportions. Let's say that we have two hospitals, and we're looking at the number of births that are recorded in one day at each hospital. Well, one hospital only records 10 births that day, 8 of the babies being female, 2 of them being male. Another hospital records 100 births for the same day, with 80 births being female and 20 births being male. Now, we have the luxury of knowing that the actual population proportion in both cases is approximately 50%. That pretty close to 50% of babies born are going to be male, and about 50% born are going to be female. So using your intuition, do you think that one of these situations is more unusual than the other, or do you think that both of these situations are equally improbable to happen? So again, if the population proportion should be 50-50, do you think that one of these situations is more unusual, more probabilistically unusual than the other, or do you think that these are equally improbable to happen or equally likely to happen? So feel free to pause the video for a second and think about it. All right, so I'll go ahead and go on here, and I'm not going to answer my thinking for A because I just want to go straight to B for a second, and then we're going to kind of come back to A. So if P equals 50%, then how much error should we typically expect to have at our sample proportions for a sample size of 10 and for a sample size of 100? So we can kind of numerically calculate the expected error in each of these situations for comparison. Because we know the standard error of p hat when n equals 10 is going to be the square root of p times 1 minus p over the square root of 10. And we also know that the standard error for p hat when n equals 100 is going to be the square root of p times 1 minus p over the square root of 100. So if I calculate those two things, P is going to be 50%, so my numerator is going to be 0.5 times 0.5, and then the square root of that, so 0.5 times 0.5, and then the square root of that is actually just going to take me back to 0.5 in the numerator for each. So this is going to be 0.5 divided by the square root of 10, which is what, 3.16. Now compare that over here. This is going to be 0.5 divided by the square root of 10, which is going to, or 100, which is just going to be 10. And so if I calculate each of these things, I'm going to get 0.05 as my standard error over here. This is going to come out to about 0.158. All right, so you might be wondering, well, what do those values tell us? Maybe like you're like, okay, I know how to calculate them, but I'm confused what they're telling me and what I'm supposed to do with them here. So what they're trying to point out here is that if I have a smaller sample size, I have more expected error in my sample proportion as an estimate of the population proportion. Whereas if I have a larger sample size, I should be getting more accurate sample proportions in general. So we can kind of apply that back over here and think. that getting 8 female and 2 male births at a particular hospital isn't that unusual, right? Because I'm going to expect a lot of error in my sample proportion, whereas in the hospital B with 100 births, this would be pretty unusual. This is several standard errors away from what we should expect to see. So when n equals 10, our standard error will be much larger. When n equals 100, our standard error will be much smaller. I'm just going to add 80% is quite unusual. And I can kind of use my standard error calculations as that benchmark for comparison, that in the case of n equals 10, 80% is only about 2 standard errors away. That's like two 15% away. But what about in n equals 100? That's 80% is like 5% away. That's like 6 standard errors away. So because the sample sizes are different, even though they're the same sample proportion in comparison to the same true proportion, this is much more unusual because this is how much error I should be seeing in this context, whereas here, this is how much error I should be seeing in this context. And so that's where we get into this idea of standardization, which we'll talk about more in the next chapter as well, is that if we think about standardizing the positions of sample means or sample proportions that I should see, that can help me kind of think about how unusual a particular sample statistic is. So again, if you remember, the distribution of possible sample means and the distribution of possible sample proportions will be normally distributed around their parameters. So I can actually assign z-scores, or z-values, whatever you want to call them, to the sample means and sample proportions that I get to talk about where they kind of fall in that distribution. So I think it's really helpful to kind of talk about this in the context of the hospital situation, that if I think about each of my sample proportions here, I can assign a z-value to identify where it falls in that normal distribution around the parameter. So what would our z-value be for the hospital A sample proportion that we got? So we got a sample proportion of 80%. We're comparing that to a true proportion of 50%. And our standard error of p hat was 0.158. So that's going to be 0.3 divided by 0.158. And that's going to come out to we'll say about 1.90 approximately. So I'm about 1.90 standard errors above what I would expect to get. So here's kind of my normal distribution, centered at 0.5. I got 0.8. My z-scale here is about 0, 1, 2, something like this. So that helps me kind of standardize where the sample proportion is falling, how unusual this is to get a sample proportion way over here, given this information about my distribution of possible sample proportions here. The hospital B example, though, is a lot more unusual because I got a sample proportion of 0.8 in comparison to 0.5, when my standard error is only 0.05. So if I do that math, that would come out to 6 standard errors above what I would expect. So if you think about that here, I don't have as much room to work with, but oh, that's really terrible. It's really hard to draw these at like the bottom of my screen. So let me just try this again. See if I can do a little bit better. Something like this. So this is 0.5, but this time we're looking at like 0.6, oops, that's way too small. I forgot. It should be like, so 0.05 would be 1 standard error. So this is like 0.55, this is 0.6, this is 0.65, right? So my standard error is a lot lower. So it's going to be a lot, I'm not going to see these values very often. So this is getting more and more unusual every 0.05 interval I go. Whereas over here, 0.45, 0.4, 0.35. So you think about where I am, I'm like way over here, right? So this is 0.8. That's just not going to happen very often if this is true. So in this case, again, even though they're the same sample proportion, the sample size does matter a lot in terms of how likely I am to see this sample proportion by random chance. And then lastly, I can just kind of plug each of these interpretations in. The sample proportion for hospital A is about 1.9 standard errors away from the population. The sample proportion for hospital B is about 6 standard errors away from the population proportion of 50%.